All right, so let me just say, I didn't go through this very slowly because I didn't think there was a need for it. We've done force problems like this in Physics 105. If it was too fast, make sure you go back in 105 and review how to do these force problems. You should be experts at them by now. All right, next topic. We want to talk about electric force fields. Now, we just call them fields, electric fields. In fact, we call them E-fields. E-fields. All right, so it's really electric force fields, but since we're lazy, we just call them E-fields. Okay. So around 1830, there was a guy named Faraday, Michael Faraday. You'll hear about him more and more. He invented this concept of an electric field, of an electric force field, in order to, well, actually he invented the concept of a field, a force field, electric and magnetic, in order to visualize electric and magnetic fields. And here's some motivation for this. So these are little, so you take some, have a chunk of iron, take a knife or something, and just, you just cut off some little tiny pieces. So these are called like little pieces of iron, so iron filings. Then you put a magnet there. What do you notice? So somehow, there's this pattern, right? There's a pattern, So something is happening to the space around the magnet. Here's another example. There's a close-up. What's going on here? There's a pattern. So something's happening to the space, around whatever this is, right? Again, these are electric things, I think. And so you see some kind of a pattern. All right, so something is happening to the space around the magnet or the charged object, all right? So he said, okay, there has to be some, he thought of this force field. A force field it's something that just helped him visualize these things, okay? All right, so what we're saying is that charges, we'll do magnetism later. We're saying charges interact with each other via the electric field. So what we're saying is that here's a charge A, and it creates an electric field. Here's a charge B, it creates an electric field. When you have A near B, the electric fields interact. And we'll talk more about that, don't worry. Okay? And how do they interact? They interact because the A will exert a force on B, and that's what's shown here, right? Of course, B also exerts a force on A, according to Newton, but we're only showing the force that A exerts on B, all right? Okay, so the force fields, the electric fields interact, and what happens is they exert forces on each other, okay? Now, so let's keep talking about this. We're going to talk about this for a while. So if it's a little fuzzy now, don't worry about it. So let's say we have a bunch of electric charges, and every single charge creates an electric field. Now, let's say, well, that's fine, but we want to know how strong this electric field is. We want to know the magnitude. Well, how are we going to do that? Well, let's say, again, like we have a bunch of charges here, and they all have these E fields, and we want to know how strong it is. Well, what if we just put a little tiny probe charge here? Or I don't care where. We just put a probe charge somewhere near the charges. What will the probe charge feel? It will feel a force, all right? It will feel a force. And then we're going to use that to determine the strength of the E field. Okay, now you may think you have no clue about this, but if you just think about it, you'll be able to do it. A proton is placed at rest in the middle of a vacuum chamber, an enclosure that's been emptied of all matter. Let's say this room. Let's say this room is a vacuum chamber, so there's no matter in this room at all. Just pretend, yeah? Consider some point X near a particular corner of the chamber, wherever. Neglect all influences other than the proton. Okay? So you have a proton, right, in the middle of the room, and then we're considering some corner where we say that's X, all right? So, neglect all influences other than the proton. At point X, what is there? So, pause your video and figure it out. Okay, we learned about forces in 105, right? We said in order to have a force, you need at least two objects. Well, here we have a vacuum chamber. We have one object, the proton. So we can't have a force, right? Because we only have one object. But we have a proton. A proton is a charged object. A charged object creates an electric field. Bingo. That's all we have. Okay? That's all we have. Now, so what we're saying again is anything that has a charge is going to create an electric field. All right. Let's say I have a plastic rod and I rub it with wool. And so the plastic rod becomes negatively charged, okay? And therefore it creates an electric field. Now, the electric field alters the space around it, just like those photographs I showed you. Okay, so here's my rod, all right, my plastic rod, and I charged it, right? I made it negative. Okay, now let's suppose I place a positive charge close to it, all right? So again, the electric field of this is going to interact with the electric field of this, and there's going to be a force, right? They're going to feel a force between them. Now here's the question. When will this positive charge feel the force? In other words, you know, I charge the rod, and then I place the particle there, the positive charge there. When is this guy going to feel the force? Okay? Now, you know, we've never considered that kind of question before, right? I mean, you know, if the sun were to explode right now, how long would it take us on Earth to feel the gravitational effects? Well, Newton actually said immediately, instantaneously. You know, you look at Newton's law of gravity, there's no time variable in that law. But think about it. I mean, the sun is 150 million meters away, 93 million miles away. Doesn't it seem a little strange that we would feel the effects of the sun if it's 93 million miles away? I mean, instantaneously, doesn't that seem a little weird, you know? And also, Einstein showed, and we'll talk about this much later, that nothing can travel faster than the speed of light. And in fact, if a photon leaves the sun, it takes a little over 8 minutes to reach the Earth. Okay? So how could it be instantaneous if the sun were to explode and we would know it instantaneously? It doesn't make sense. All right? Well, the answer, which we're going to talk about later, is that electric and gravitational fields travel at the speed of light. Okay? So in other words, when I put this plus charge there, it's not going to instantaneously feel the force. There's going to be a little bit of a time delay. Now, come on, it's not going to be much of a time delay, right, if the field travels at the speed of light. But if this is on the other side of the universe, there's going to be a bigger time delay. But all I'm saying is it doesn't happen instantaneously. Okay, so here we go. So this is the field model, Faraday's field model, where things don't happen instantaneously. So we have this charge Q1. It produces an electric field E1. We have a charge Q2. It produces an electric field E2. It's the electric fields that interact. And you might think we're making a mountain out of a molehill or we're making this hopelessly complicated, but you have to, because this agrees with relativity, which we'll talk about later. All right, Einstein's theory of relativity. This is Newton's model. It was called the Newton's action at a distance model. It just said that Q1 interacted directly with Q2, and it happened instantaneously. Well, I'm sorry, it's wrong. Okay, it disagrees with the data. It disagrees with the relativity. All right, what are you going to do? Okay. All right, let's see. Okay, so here is a positive charge, and again, it creates an electric field. And what we've learned by experiment, as if you get further and further away from the positive charge, the electric field gets smaller and smaller and smaller. All right? So two things. From a plus charge, the electric field points away. All right? Number two, when you get further and further away, the electric field gets smaller. So see here, we're really close, right? So this vector, okay, it points away, and the length of this says that the electric field is strong, all right? Now here, we're far away from it, right? So this is the direction, but the length of it says that the electric field is smaller than this one, and so forth and so on. So what I'm saying again is that electric field is a vector field, right? There's a magnitude and a direction. It's a vector field. These lines are called electric field lines. I mean, they don't exist. They just give you an indication of, of the direction and the magnitude of the electric field, all right? So these are called electric field lines. That was kind of what Faraday came up with, all right? But they're super useful, because now you know what the direction of the E field is. Okay, in the 1860s, Maxwell from Scotland, he looked at all of the experiments that have been done with electricity and magnetism, and he wrote the mathematical theory that combined everything. And it's always important to have a mathematical theory because, number one, you can explain everything. Number two, you can predict new things. So his mathematical theory actually contained 20 equations originally. And then over the next, 60 years or something like that, other people worked on these equations, and they combined them into 4. So here they are. Now, I don't know what the deal is with this projector, but those integral... All right, you don't even know what I'm talking about, right? Because you haven't had calculus. This is an integral. Don't worry about it. Don't worry about this. Well, first of all, it's supposed to be like that. But if you don't know what it is, don't worry about it. The only reason I'm showing you this, look at this is Maxwell's theory. This explains everything there is to know about electricity and magnetism, classical electricity and magnetism. And what are they written in terms of? Electric fields and magnetic fields. All right? So all I'm trying to say is electric fields and magnetic fields are incredibly important, because Maxwell's equations, which describe everything there is to know about classical electricity and magnetism, are written in terms of these fields. So fields are important, and they're real. All right, they're real. All right, now let me try to explain a little bit more what this electric field is. Okay, so we wanted to find, I've been talking, but now we wanted to get a definition of the electric field. Okay. Here's a picture of a fish, and it's dead. And it's been in the sun for quite a while. So what is this dead fish's most obvious and unpleasant property? It stinks. Okay, very good. Now, how would you measure the strength of the smell? Well, you'd use a nose, right? All right, you use a nose. Now, does the nose have anything to do with the source of the awful smell? No, not at all. The nose just measures the smell, right? All right. Here is a positive charge, Q. It produces an electric field, and I have all the electric field lines shown. How can we measure the strength of the electric field? Now you think about it for a minute. So pause your video and think about it. What can we use to measure the strength of the E field? Okay, what did we use to measure the strength of the stink? We used our nose. So what are we going to use to measure the strength of the E field? So pause your video and think about it. All right. Well, so we need something like a nose, right? So what are we going to use? Well, I already told you a couple minutes ago. We're going to use a little charge, we call it a test charge or a probe charge. We'll call it Q prime for no good reason, right? So Q prime has to be super, super small because we don't want this to have any effect on this, right? So this is going to be positive, just for no good reason. This is going to be positive, and I know that this repels that, but if this is super, super, super small, it's really not going to have much of an effect on that, okay? So this is like the nose, right? This is like the nose, okay? Now, wait a second. what is this going to be able to measure? Well, you have a Q here and a different Q here. What's going to exist between a Q and a Q? A force, right? A force, you know? So you put this charge here, you have two objects, you can measure the force, right? You can measure the force. So if this is a really, really big Q, you know, it's going to have a bigger force than if this were a little q, okay? So this probe, or this test charge, will be able to feel a force, all right? And that's going to give us an indication of how strong this E field is. Now, does this probe have anything to do with the source of the E field? No! This is what's creating the E field. We're just using this to measure it, you know, just like the nose. Okay? All right, so let's define the E field. So the E field is going to be the force that the probe charge feels divided by the probe charge. Okay? Now, why do we want to divide by the probe charge? Because the E field only depends on this, right? The E field doesn't depend on the nose, you know? And so we've got to divide out this, so the E field only depends on what created it. Okay? So we get rid of this because we don't want this, because this has nothing to do with the E field. All right. So let's do a super easy example. It's like the easiest example you can come up with. So this is called a point charge, right? It's a point charge, okay? So we want to find the electric field for a point charge. And when we talk about magnitudes, I don't care about, we know the direction, right? It's away. All right, well, I mean, first we'll just get the magnitude, then we'll talk about the direction. All right, so here we go. So the magnitude of the E field is the magnitude of the force divided by the probe. Okay, well, what's the force? Coulomb's law, right? Coulomb's law. So the force is K, charge number 1, right? That's this guy. Charge number 2, the probe, divided by the distance. Let's call this distance, I don't know, d or something like that. Divided by d squared. But then we divide by the probe. So what do you get? You get K, Q over d squared. Now notice, this only depends on the charge that created it, right? Which kind of makes sense. The stinky fish, the smell of the stinky fish, only depends on the stinky fish, right? But also notice, so it depends on the charge that created it, but notice this, as you get further and further away, the electric field gets smaller. Same with a fish, right? If you move away from it, you don't smell it as much, you know? So there you go. The electric field of a point charge is K, that's just that constant you see all the time in electricity. Q, the charge that created the E field, divided by distance squared. Now for a positive charge, you know, the E field points away, right? Away. And so here's the real complete answer, right? So this is magnitude, right? I don't have any vectors. So this is the vector. So the electric field vector of a point charge, here's the KQ over R squared. By the way, sometimes you put D squared, sometimes you put R squared. Who cares? It's just the distance, you know, away from it. And if it's a positive charge, the E field lines point away, right? Away. Okay? How about a negative? Well, guess what? Towards, right? Towards, okay? Does that kind of make sense? I hope it makes sense, right? Because we're always assuming that this charge is positive, always, just to make things easy, right? Just always positive. So if this were negative, you know, these lines would point this way because, you know, this thing would be attracted, right? It'd be attracted. Okay, so for positive, KQ over R squared away. For negative, KQ over R squared toward. All right. And, okay, what if we have more than one point charge? Well, again, this is a vector, right? So you just add vectors, just like we did in 105. That's nice. All right, so here's an example of that. Okay, so what is the direction of the E field at point P? So this is a positive Q, that's a negative Q. By the way, when you write it like that, it means that the magnitude is the same, right? Because this is a Q and that's a Q. Just this is positive, that's negative. All right? So use this and also the directions that you learned and figure it out. This is really important, so pause your video and figure it out. Okay, so the E field from the plus, okay, all we care about is at point P. So, I mean, I don't care about all these things that go like that. So the E field from a plus is this way, and this is not, you know, this is close, so it's going to be this way, and it's going to be strong. Now the E field from a negative points towards a negative. Now this distance is much more than this distance, so the E field at this point P from this guy is going to be weaker than that guy. And it's going to point away. So here. So this is the E field from the plus, right? It points away, and it's strong. This is the E field from the minus. It points towards the minus, and it's weaker than this one because it's further away. So you have this that way, you have this that way. So what's the net, or what's the sum? Well, that way, right? That way. Just good old vector addition or subtraction, however you want to look at it. By the way, this is called, remember, this is a dipole, right? Because they have a plus and a minus. And we'll talk about we'll use dipole a lot. And the reason we do is because they appear in nature a lot. All right? So that's the electric field of a dipole. But I'm going to be careful. It's the electric field of a dipole along this, you know, at this point P, right? All right. Let's do another one. Okay, that's another dipole, but now we don't have the point P over here. We have it over here. All right, so what's the direction of the E field at point P? So do the same thing. So pause your video. You have to understand this concept. So pause the video, draw your E field lines, and figure it out. All right, let's answer it. Okay, so the E field points away. All we care about is it here, right? So it's going to go like this. Here, the E field points towards it. All we care about is it here, so it's going to go like that. So you have one E field going like this, you have the other E field going like that, and then you just do the vector addition. So here's the E field plus, here's E field minus. So what would you do? You'd resolve this into components this way and that way, this one, that way and that way. This would cancel that, this would sum to that, and you just get the net there. All right? So make sure you know how to do this. All right, let's talk more about this electric force. All right, so let's say we have a vacuum. So there's nothing in it, nothing here, except for this Q. All right? So we have a point charge Q in a vacuum. Okay, just minding its own business, you know, just sitting there. Then all of a sudden, we create a nearby external E field, all right? So we put this plus Q here. And this plus Q, you know, creates an E field, right? Yeah, we know that. Okay, well, here's the question. What is the force that this guy feels? Now, we already know the answer, right? I mean, one answer, just use Coulomb's law, right? But we want to write it differently. So Coulomb's law is just K, the charge number 1, charge number 2, divided by the distance squared. No kidding. All right, but now we want to write it differently. You'll see why. So let's do it, write it differently. All right, let's do. Okay, so there, whoopee, right? So I added some parentheses, whoopee, right? Now, wait a second. What is KQ over the distance squared? That's the electric field of this Q, right? So this thing here is just the electric field created by that big Q. So therefore, this is just Q times E. All right? This is a big deal, all right? And here's the vector version. So this equation we're going to use a lot, all right? A lot. And so you want to know it, right? So, but you have to understand what it means, though. What it means is you have an external E field. You put a Q somewhere nearby, and this Q is going to feel a force given by this equation. All right. So let's do an example. Does this look like Physics 105 or what? All right, so we have an electric field that points to the right, and it causes this object here to move to the right. And it hangs at a certain angle, so it's not moving. What's the charge of the ball? Oh, look, the ball has to be charged, right? If it were not charged, the electric field, I mean, there would not be an electric force on it, you know? And so the fact is that there's an electric field this way, and it's moving this way, and we know this equation. We know that F equals QE. Well, E points to the right, Q is positive, so therefore F has to point to the right. Awesome, okay? So we know that this thing has to be a positive charge. All right, so here you go. So what are you going to do? You're going to draw your force diagram, just like we learned in Physics 105. So let's draw the force diagram. So here's the object is the charge, right? All right, so what are the forces on the charge? Well, we have an electric force to the right. Here we have a tension, right? This is a string, so we have a tension this way. We have tension this way. Tension, here's our angle. And of course we have mg. All right? So how are you going to do it? Just like we always do it. So sum of the x forces. So what's the sum of the x forces? So, okay, wait a minute, but what is QE? I mean, sorry, I can't believe it. What is FE? It's QE, right? Because they give us, look at it, they give us the electric field. So we're going to use this equation, F equals QE, right? So the sum of the x forces, we have QE this way. Now we have this crazy tension. We've got to resolve it into components, right? All right, so we want this guy, so it's sine. So it's minus t sine theta. That equals 0 because it's not accelerating. It's not even moving, right? Then we have the sum of the y's. So we have, this is t cosine theta. Then we have minus mg equals 0. All right. So this one says that QE equals t sine theta. So you look at, so we're trying to get Q, right? That's what it says, find the Q. So here I say QE equals t sine theta. Now we know E, we know theta, but we don't know T, right? We don't know the tension, so we need another equation. Well, this one just says that mg equals t cos theta. Right? Okay, so you can solve that however you wish. I mean, it's just algebra. I'll show you what I'll do. I'll show you my method. Doesn't matter. Doesn't mean it's any good. I mean, you can, again, really, you can solve it however you want to solve it. All right, so this is what I would do. So I would say that, I don't really need that. So I would say that QE equals t sine theta. Now I'm going to divide this by mg. Well, if you divide it on the left, you got to do it on the right. So I'll divide that by mg. But wait a second. Mg equals t cos theta. Right? Yeah. And what's awesome about this is that the t's go away, right? The t's cancel. And what's sine over cosine? Tangent. So you get QE over mg equals tangent theta. So then you just solve for Q. So therefore Q equals mg tan theta all over E. Ta-da! All right. So that's just your typical Physics 106, problem, which is kind of like Physics 105. All right. So you should expect to be able to do some of these problems, Okay, let's talk about these electric, we got to quit. Yeah, let's quit.